Hello, everyone. Good morning, good afternoon, good evening, everyone. I'm Zhijian Ou from the Electronic Engineering Department at Tsinghua University. Welcome to this online lecture organized by the department. It is the 9th forum on electronic information science and technology. It's also the first lecture in speech and language technologies frontiers lecture series. We hope these lectures can promote sustainable academic communications and interactions, especially in the new situation of COVID-19. Yet the pandemic make physical meeting difficult, but virtual meeting can still keep us together and help us to know each other. You can participate in the lecture by Zoom. At the same time, the lecture is also live streamed so that you can watch it without Zoom. It is our great honor to invite Professor Paris Smaragdis for today's lecture. First, allow me to give a short introduction to Professor Paris Smaragdis. Paris is a professor and associate head at the Computer Science Department at the University of Illinois at Urbana-Champaign. He obtained a PhD at MIT. In 2015, he was elevated to an THUEE Fellow for contributions in audio source separation and audio processing. I skip the many honors Paris has received during these years. He is currently the editor-in-chief for the ACM IEEE transactions of audio, speech, and language processing. So let's welcome Paris for this distinguished lecture. So Paris, please.
Thank you very much for having me, and thanks for the kind introduction. And it's really an honor to be invited and speak to so many people. This talk it's supposed to be about some of my ideas on things that people should be thinking about and things that people shouldn't be thinking about when it comes to audio. Hopefully you'll find some inspiration out of it. But the plan is going to go as, whoops, hold on, close my window here. The plan is going to go as follows. I'll talk a little bit about sort of current trends in audio signal processing. And then I'll talk about some of the issues that I have with that, and then sort of give you a little bit of how I like to think in terms of sort of coming up with new problems and how that can result in things which are a little different from what a lot of the people might be working on. So we'll get into details. Don't worry about the outline here. And usually when I give a talk, I love it when people interrupt me and they ask questions, but I realize it's going to be a little more difficult to do in a streaming manner. But I do have the chat window open if you're in Zoom, and I'd be happy to take any questions as I'm going through the talk. All right, just to give you a little bit of an introduction, the area that I'm working on is called machine listening. The idea is to make computers that can understand sound. So we basically start with something where we're given a signal like this waveform over here, and what we're trying to do is make systems that can tell us what's happening there. Is it speech? Is it noise? Is it music? Is it happy? Is it sad? Does it mean something? So it's a very fascinating field because it really brings together a lot of different disciplines and a lot of sort of fields of science. So if you haven't played much with it, I strongly suggest you do, because it's really fun to be in. And just to sort of give you a sense of the sort of two main interests that I have in that field, the first one is that I'm really interested in finding new ways to process and understand sounds. Of course, audio processing has been around for a long time. We have a lot of really strong established algorithms out there. But what I'm really interested in is sort of trying to expand the way the toolkit of what we use and how we use it. And sort of the big science question that I have is, how do we make machines develop their own sense of listening intelligence on their own? And to me, that's the big science question when it comes to sound. And the story that I usually say is that, a few billion years ago, my great-great-great-grandmother was a single-celled organism. She didn't have ears or eyes or, any kind of senses. But by being bombarded from, with sounds and sights and, all sorts of stimuli, it ended up developing all these, wonderful ways of understanding the world around it. So what I want to do is the same thing, but in the digital space, and hopefully it's not going to take a couple of billion years. But I do want to have be able to design machines that they get exposed to, in my case, just sound. And without any supervision, they slowly start doing the things that we do when it comes to understanding sound itself. So that's the big science question. And then in terms of the engineering questions that I have, I'm really interested in thinking of new ways of working with audio, not necessarily use the standard representations and the standard ways of thinking that have been around, but mostly playing around with new ways of doing things. And my inspiration from that tends to come from a lot of my friends from physics and math, because whenever they talk to me about the latest trends, they always have these strange mathematical things that I don't understand. Whereas the math tools that we use in the audio world have been set in stone since 50s or the 60s and haven't changed that much. So these are sort of the main two things that I want you to keep in mind as I'm going through the talk. Just to give you a little bit of a sort of an overview of my sort of take on what's happening right now in the world of audio processing. Like many other fields, deep learning has been taking over a lot of things that people do in audio and speech. Most of the standard tasks, whether it's denoising or removing reverb or restoration, declipping, and all of those things, they've all have been delegated to deep neural networks. In the plot that I have on this slide, what I'm actually showing is submissions from the titles from submissions from ICASP 2019 for the audio track. And what I found to be very interesting is that the 2nd, 6th, and 10th most common word in titles were neural, deep, and network, even more so than other words which are you would expect to be more dominant in the world of audio. So it's really something that's been taken over. And of course, it's a very convenient kind of pipeline, right? Because the way that it usually works is that you get a big training data set, you design a network, then you let it train on the data, and then you have your solution. You don't have to think very much, which is a good thing and a bad thing at the same time. The nice thing about it is that it's really driving a lot of the thinking about audio processing in a towards a common pipeline. So if you think about it, the way that standard audio processing used to work for many, many years is that you would have, let's say, a sound that you wanted to somehow change or enhance or do some kind of processing on it. You would put it through some kind of a filter bank and subsample, usually the short-time Fourier transform. Then you would do some kind of processing in the frequency domain, and then you would do the inverse short-time Fourier transform or some other kind of sort of a filter bank, and you would get back, the output that you desire to get. And the way that the model has changed right now is basically almost a one-to-one mapping of these operations, but in using neural net terminology. So instead of having a filter bank, we would have some convolutional front end. Instead of subsampling, we have some striding or max pooling or something like that. Then the process itself gets replaced by a neural network, and then again we have sort of this transpose convolutions and upsampling that gives us back just raw audio. And if you look at all of the modern systems for denoising, reverberation, enhancements, a lot of those models basically use exactly this type of a pipeline. And it's great because it makes everything be very similar, and it also gives us a connection to what people have been doing before neural networks. But I do have a bunch of issues with this. So the issues that I would like to raise is that now there's this shift in our field where instead of sort of looking into signal processing algorithms, instead of thinking hard about what would be a good way to solve a specific problem, we basically end up doing a lot of random hacking where we just collect a lot of data, just use a network, and eventually it's going to figure out how to solve the problem. And of course, that's a bit of a problem, especially for younger researchers and students, because they have this dilemma that, well, I could do a lot of machine learning, but a lot of it is just searching for the right architecture and the right data sets. Or I could do signal processing, but it tends to be very limited in the kind of outputs that it can produce. But what I'm going to try to advocate in this talk is that there's a lot of fertile ground in between. You don't have to be fully rooted in any of these two areas. The other thing that I don't like is that this shift towards machine learning, especially deep learning, introduced a very sort of annoying distraction in the field, which is now it's becoming very easy to solve difficult problems. I was working, for example, in speech enhancement since I was a graduate student, and we didn't really have a lot of progress for 20 years. And then suddenly, as soon as we started using deep learning, the problem is pretty much solved. And that happened just in 3-4 years. So it's amazing that we're solving all of those problems, but one of the issues that I'm seeing out of this is that a lot of paper submissions, a lot of work that's being done by students ends up chasing metrics. And that's not good, right? Because I don't want to see yet another neural net architecture to solve an existing problem. What I'd like to see is new ideas or new things to try or new things to learn. So this ease of use in our field has really made for a lot of papers that are not as interesting as papers used to be. And in general, whenever I talk, at least to my students, I always urge them to avoid this line of work. Be the first one to solve a problem, but then move on to something else. There's no need in sort of competing in that space. There's no need in chasing metrics because that's not really where the interesting science is. So what I'm going to do sort of for the remainder of the talk is go through sort of my process on, how do we come up with interesting questions and how do we sort of avoid chasing all of those metrics and try to do things which are not necessarily sort of a standard sort of deep learning. And the best way that I found to do that is to always find a motivating problem that's really difficult, very, very high level, and then you use that as an inspiration to come up with ideas. So in my case, what we have is a project called the Hearables project, and the idea is to do audio augmentation in real time. So the ultimate goal of that project is that we're going to have some kind of a smart device that's going to be sort of inside your ear, like an earpod or something. And its job would be to basically take all of the sounds that are coming to you and then changing whatever you're hearing to best suit what your needs are. And that might mean that it would have to sort of do things that a lot of existing devices do, but it could also do things which, we're still not quite sure how to do. Now, of course, there are a bunch of challenges here. The audio problems that we want to solve are difficult enough, but now we're going to have to be solving those things in real time in a device that has to fit inside your ear. So it becomes a very, very difficult engineering problem, but that means that that's a good thing because it gives us a lot of problems to actually solve. So in terms of the things we want such a device to do, there's the obvious feature list. For example, we want it to be able to react to your surroundings. If there's a lot of loud sounds, you want it to suppress it. If it's very quiet, you want it to help boost. You want it to be able to sort of remove noise or equalize the sound to suit your, your hearing sort of abilities, or maybe deal with any sort of hearing loss issues that you have. And you also want it to be able to attend to things, right? It should be able to monitor your heartbeat, for example, because it's easy to do from the ear, or you can listen for, your breathing rates and stuff like that. These are obvious things, and you can already find devices that do that. It's not particularly special. What we're really interested, though, is things which are much more complicated and require a lot more sophisticated processing. So we would like a device like that, for example, to be selective in picking what sounds you should be hearing and what you should not be hearing. So for example, if I'm in my home and then, I have a baby in another floor and it's crying, I want that crying to be amplified because I need to attend to it. But if my neighbor's baby is crying, I probably don't want to hear that. So now you need to have a device that's able to figure out what are the sounds that are coming to my ears and then figure out which ones to keep, which ones to throw away, and then also process the sounds so that it can do that as well. We want to be able to have it play sounds virtually all around you. We want it to be able to sort of identify sounds as they're taking place. And we also want these devices to be able to collaborate with each other. If I go in a concert and there's 1,000 people who are also wearing devices like that, it would be really good to be able to use all of them as a microphone array and then be able to get even better audio coming out of it. So a lot of very, very difficult problems. But again, the goal is not necessarily to solve everything. The goal is to find inspiration. Just to give you a sense of what we mean in terms of sort of augmented audio, here's a simple example. And this is going to be a little, this is going to be a video demonstration. Don't worry about the visuals. Just what I want you to do is just listen to the sounds. So I'm going to play this video, and there's basically going to be 4 sounds which are dominant. There's Kevin's voice, Irene's voice. You're going to be hearing a lot of humming noise coming from the air conditioning unit, and you're going to hear some music coming from Kevin's laptop. So here's the video.
Your music is too loud. Can you turn it off?
Oh yeah, I'm sorry about that.
All right, thanks.
Yeah.
Now you could imagine that if you wanted to enhance the scene, maybe you just wanted to remove some of the sounds but keep everything else, right? So an augmented audio version of that video would look like this, or at least one version of it would look like this.
Oh, yeah, I'm sorry
Now,
about
if you were
that.
paying attention, what happened here is that Irene's voice was removed, but also the humming from the AC was removed. But at the same time, Kevin's voice or the music playing in the background wasn't necessarily harmed. So these are the kind of things that we want to do with a hearable device. The only catch is that we have to do this in a device that fits inside your ear and doesn't drain the battery or doesn't become extremely hot. So what's really nice with this problem is that it's a problem that generates new problems. So we need to have efficiency, we need to have responsiveness, we need to be able to scale, we need to do interesting distributed processing. And the focus that we're going to have on that project is not necessarily improving on the metrics. We don't want the best source separation or the best denoising or the best virtual placement. What we need to do is to do it under the constraints that we have to have in place. So for the remainder of the talk, what I'm going to do is basically talk about four sort of sub-projects that got spawned using this. And hopefully they'll give you an idea of sort of the thought process that I have when it comes to coming up with new problems. So the first thing I wanted to talk was trying to get efficiency. So like I said before, this is a device that's going to be really, really small. It needs to have very low power requirements. It needs to, not be very hot. We don't want to burn anybody's ear. And it needs to be able to work for hours without being recharged, right? So that means that we need to do computations extremely efficient. This is a little bit older work that we did, but again, it's something that we've used for this kind of device. And what we did is we developed a set of neural networks that was sort of an extreme case of quantization. And what we did in those networks is we made sure that all of the network parameters and all of the data that was exchanged between all the layers was binary valued. There were everything was either a 0 or a 1. Now, what that means is that when you come to designing the hardware, you don't have to worry about doing any complicated arithmetic or dealing with floating point or fixed point or any of those things, which can result in substantially complicated hardware. Everything could be simplified by using just bitwise operations. So the simplification that was made was the following. If you were to take a standard neural network, you would have the equation that we have at the top, standard layer. Your inputs are X. This would be sort of a floating point vector coming in, for example. You would do a dot product with your parameters and then put that through some kind of a nonlinearity. Traditionally, would be a hyperbolic tangent or a sigmoid, and then you would get your output. Instead, what we're going to do is we're going to come up with an extreme quantization of that, and we're going to say, well, we're just going to represent our data X as just binary values. It's either going to be 0 or 1. So let's say all the negative numbers will be 0, all the positive numbers will be 1. And then we're going to do the same thing for the parameters. So now we're going to have a binary vector X and a binary vector W. And instead of taking the dot product, what I'm going to do is I'm going to take the XNOR between those two. And that's basically a quantized simplification of the multiplication process, right? If the signs are the same, you get a 1. If they're not, you get a 0. And then instead of passing it through a sigmoid, which effectively tells us, if you have a big number, give me a +1. If you have a small number, give me a -1. Instead, we're going to see if more than half the bits are set on or off by basically seeing how many of those are on. And that will tell us whether we have most of the values of this sort of sum of XNORs being set to bit 1, or most of them being set to bit 0. So that's an extreme quantization version of the original equation. So graphically, what that would mean is that in a real valued network, you would have a matrix. Somebody would give you an input. You would take a matrix product between the two. You would get some vector. You would have to apply some kind of a nonlinearity on it. And that would be the output of the layer. And all of those things would be floating point or fixed point operations. With a binary valued network, your data now is going to be just bits. It's going to be the 0 or 1 for every parameter and every data point. You'll be doing an XNOR as opposed to a multiplication. Those things are trivial to do in hardware. And then instead of putting data through a sigmoid, we basically try to count how many of those sort of values that we get out have a majority bit set. And then our output would be basically this, whether the majority bits were set or not. So again, very, very simple type of processing. And what's nice with it, it results in really, really simple hardware. So in this case, you can imagine one connection between two nodes in a neural network. In real life, or sort of in standard networks, would be a 32-bit real value multiplication, which is a fairly complicated circuit. In our case, it ends up being just a simple gate. And then if we start scaling this up to more and more complicated networks, we notice that we get extreme savings in the computational complexity, but also in the amount of memory that we have to use. Now, what makes it even more interesting is that if you actually try to design the hardware for this, you get even more extreme benefits. For example, for a network about that size, we sort of made a design on hardware, and if we were to use 32-bit floats, you would need about 6,000 square micrometers for that circuit. If you were to use the binary version, you would only need 100. And the power consumption of the floating point unit, again, would be 2,000 microwatts, but it would be 20 microwatts for binary. So from a hardware design perspective, we're getting 2 orders of magnitude improvement, which of course is really good. Now, the question is, if we do something like this, does it work? So just to give you a very, very simple example, we try to do this for things like speech denoising. We use a standard noisy autoencoder. You give it noisy spectra, and you want it to produce a clean spectra coming out of it. Very standard, very simple setup. And what we're going to do in this case is we're going to take a real value representation. We know we can't feed this as is to our network because it expects zeros and ones. So instead, every pixel of the spectrogram we're going to represent as a 4-bit number. So now we're going to get 4 times the dimensions. We're going to put that in a binary network, and then its output is going to be a binary mask. And if we do something like this, what we're seeing is that the performance is only slightly worse than if we were to use a real valued network. So the dark blue lines that you're seeing here are performance metrics for a regular neural network for a simple denoising task. The bigger the numbers, the better. The light blue bars that you see are going to be what the binary network did. And what you'll notice is that, of course, it doesn't match the performance, but it's only a little less off. The advantage of being that little less off, though, is that we're gaining a simplicity in the hardware that's in the order of 2 orders of magnitude, which, of course, is a great thing. And it means that we can actually run those algorithms in a tiny device. So the take-home message from this part is that, again, looking at the hardware and looking at the constraints that we have can help us inspire sort of new approaches for doing processing. This is not something that's going to be faster in software. In fact, it's going to be a lot slower in software because software is designed for this kind of processing. But it is extremely faster in hardware and much, much simpler. It doesn't give us the best possible performance, but it gives us better performance at metrics that are not really used a lot in this kind of line of work. And of course, from a scientific perspective, it opens up a lot of interesting research ideas. We can start talking about binary signal processing, about sigma delta processing. We can start processing data in a sort of a pulse density modulation space as opposed to the standard PCM that we're doing. So there's a lot of interesting questions we can answer there, and lots of interesting papers to write. So that was sort of part 1. Now, part B, I want to talk a little bit about responsiveness. So this is a project that we call AutoDSP. It's been going for the last year and a half or so. And the goal here is that if you were to have a device like a hearable, you want it to be able to adapt in real time. So that means you're going to have some kind of adaptive signal processing going on in it. The problem with an online adaptive algorithm is that they require a lot of fine tuning. They're not very easy. If you read about them in a textbook, there's a very simple way of defining them. The solutions are very clear, but making them run on streaming data, it's something that's not very easy. And in fact, most of the work being done in that field is trying to figure out what's the best way to do this kind of sort of online sort of adaptation. So what we did in this project is we actually started using meta learning for signal processing. And the idea is to replace the existence of an experienced audio engineer that tries to fine tune the algorithm and have this thing be an automated process that's done by gradient descent. And the goal here is to learn online optimizers that will learn to sort of tune adaptive filters in any system like that. And the hope is that those optimizers are going to be smaller and faster and simpler, and they would generalize much better than all of the custom solutions that we do now by hand. So just to sort of show a little bit of the details, here's the traditional approach when it comes to doing adaptive filtering. You're going to have what we're going to call in this context an optimizee, and that's going to effectively be a function that applies a filter. So for example, this could be your denoising filter, it could be your echo canceller, it could be any kind of adaptive filter that you want. And you're going to define some kind of a loss function that measures how well that filter is doing its job. And then what we're going to do, if we want to apply this in a real life situation, we need to define what's called an optimizer. And the goal of the optimizer is to tune the parameters of your filter is theta. So we want to tune the parameters of that filter theta to optimize your loss function. There's a lot of different kinds of algorithms we can use for that. For example, LMS is the standard textbook algorithm. In real life, you probably want to use something like normalized LMS or RLS. And there's, again, no shortage of different ways of sort of optimizing those things. But essentially what the optimizer does is that it would take the gradient of your operation. It's going to have some kind of a state because it usually wants to remember what happened in the past. And then using these two pieces of information, it'll tell you how to update your filter. And that's going to be a very crucial thing, right? Because if your filter is not adapting fast enough, it means that you won't be able to catch up with the task that you have to do. If it's adapting too fast, then it might give you a lot of wrong results because it might be overshooting. So it takes a lot of tuning to figure out how to take the gradient and sort of maintain the states and be able to translate that into reliable sort of updates for your filter. Now, this part of tuning the optimizer is really the magic part in a lot of algorithm design. It requires a lot of expert man hours. Most of the time you're going to spend as an audio engineer, if you're doing a lot of adaptive filtering, is going to be in trying to figure out the optimizer. And that is really the big deal in all of the companies, right? This is the secret of the technology. It requires a lot of extensive tuning. It's going to be different for different filters. It's going to be different for different tasks. It's going to be different for different devices or contexts. So it's a very, very difficult problem and very, very time consuming. So let's look at a simple example and sort of try to come up with a concrete case of how you would try to solve something like that using this kind of processing. And to do that, we're going to use the echo canceling example just because it's a sort of a well-known one and a simple one, and I'll be able to show you exactly how this works. So echo canceling is an extremely common operation that happens in speech communications. In fact, now that we're all doing a lot of communications via Zoom, we're all very well aware of it. So what is the problem? Well, let's say that I'm having a Zoom conversation with you. What happens is that I speak, a microphone picks up my voice. That's going to get transmitted over to your side. It's going to come out from your speakers. If you're not wearing a headset, what's going to happen is the sound from your speakers is going to be fed back inside your microphone. That's going to get transmitted back to me, and it's going to play back from my speakers. So oftentimes, when echo cancellation isn't working well, what happens is you speak, and then you hear your voice coming back from your speakers after some delay. And that's something that's very, very annoying, of course, when you're trying to say something. So the goal of echo canceling is to have some kind of a filter whose job is to take the input from your microphone and then take the signal that's coming back from the far side and try to figure out how can it filter the input that it's recording locally in such a way that if you subtract it from whatever is being received, you get to cancel out as much of the noise as you can, as much of the feedback as you can. It's not a simple problem, especially in real life, because you have nonlinearities. You have a lot of transformations that happen as your voice gets captured, gets sent over, and then gets recaptured and sent back. But it's something that works relatively well. That said, again, most of us still prefer to wear headphones just to avoid having this coupling between the speaker and the microphone, right? Because it doesn't always work great. Now, the key in making the system work is going to be the optimizer. And what the optimizer is doing is it's keeping a track on what the input is and what the received far end sound looks like. And it's trying to figure out what is the best filter or how to guide the adaptation of the filter so that your echo canceller does its job the best. Now, if you were to look at the standard textbook solution, the way that you would solve it is that in this context, we have to define the optimize. Again, that's going to be the process that does the actual subtraction of the feedback voice. In our case, it's going to be just some kind of a filter in the frequency domain. So again, U is going to be your voice as it's being captured. There's going to be some filter that we apply on that, and that's going to give us basically a resynthesis of your voice with all of the propagation effects modeled by the filter. And then what we want to make sure is that when we subtract that, or the difference of that versus the signal that's coming back to us from feedback, gives us a zero difference. If that's zero, that means that we're canceling out the feedback, and it means that we're not going to be getting any echo. If this is not close to zero, it means we're not doing a good job, right? So the optimization problem is try to find your filter W such that you minimize this cost function. So standard way you would solve this problem is that you would have to define an optimizer. So the sort of simplest one we can come up with is we can just basically take the gradient of that operation. which is very simple. And then we don't want to use just the gradients to adjust the weights. We're going to multiply that by a small number, usually called the learning rate. And then that's going to give us the update. So the overall form of the algorithm is going to be get the gradient, put it in the optimizer. What the optimizer is going to do is take that gradient, multiply it by a small number to make sure we do a small step and we don't overshoot, and then subtract that from your filter parameters, and that's going to be your adaptation. Now, of course, in real life, you wouldn't do something as simple as just scaling by a number. You would maybe have some momentum term. You might do some normalization. There's a lot of variations of that, but all of those variations effectively do some kind of processing of the gradient. Now, the way that we're going to solve this problem is going to be a little different. Well, we're going to still take the optimizee and the loss function being the same. We're still doing our optimization there the same way, but now we're going to have a trainable optimizer. And what we're going to do is we're going to say, let's take the gradient, but now instead of us deciding if we have to clip it or have a momentum term or learning rate or anything like that, instead of that, what we're going to do is we're going to put it in a neural network, and we're going to try to train that neural network to give us the best possible update for our weights. So now, how we translate the gradients to a weight update is not going to be a deterministic standard textbook thing that's using a lot of tricks that we know. It's going to be a learned process. So that means that now we're going to have a meta-learning algorithm, where the idea is that we're going to have an inner loop. And what's going to happen in the inner loop, we're going to have a whole bunch of echo cancelers working on different problems, and they're going to be trying to solve these problems, and they're going to be guided by a neural network on how to adapt their weights as they're seeing sound coming in. And then there's going to be an outer loop that after some of those echo cancelers try to do echo canceling, we would look at how well they worked, and then would use a sort of regular gradient descent to figure out how to adjust our optimizer to help the adaptation be better. So what that means is we're going to have two loops. There's going to be the inner loop, where we're going to be applying our filters and updating them based on what the optimizer state is right now. And then once we're done with the inner loop, we're going to collect a lot of the information of how well all of those echo cancelers worked. And then we're going to have this outer loop where that information is being fed into a regular optimizer, whose job is to figure out what's the best way to adjust the translation of the gradient to an update for our weights. So we're effectively learning the optimizer. Once that is done, at runtime, we just freeze the optimizer. And then if we're trying to do, for example, echo canceling, we set up a filter. And then every time we get some data, we get the gradient, and then we feed that to a neural network. The neural network tells us how to adjust our weights. And then we adjust them that way. And then it becomes a regular sort of feed-forward process. So the complexity is going to be roughly the same as a traditional system. The echo canceling is still done by a linear filter. But instead of updating by some simple heuristics operating on the gradient, we're going to have a neural network operating on the gradient. So after we do that, the question is it worth it? Well, let's look at some of the results. What we did is we used a very small optimizer model. It's just 2-layer GRU with 48 complex valued units. We only trained on 1 hour of data for echo canceling. And what we've done with that network is that it was a sort of element-wise translating gradients to filter updates. We used the Microsoft echo canceling challenge to sort of use data for that. And we tried to compare that with all sorts of different algorithms. So let's focus first on the plot, which is down here, the lower plot. And what you're seeing in this plot is the performance of our echo canceller as it was adapting across time. Every color line that you see is going to be a different type of an algorithm. So for example, the thin gray one here is going to be the standard textbook LMS. And for all of those algorithms, what you're seeing is that as time goes by, the optimizer is doing a better job at getting better performance. The higher the value, the better the performance is. So again, we start from 0 dB because the canceling is not happening. And as time goes by, everything improves. And then what happens in this pink region over here is that we have a scene change. For example, maybe the microphone moves or the speaker changes, or somebody else starts speaking, which means that we have to forget our filter and then retrain it from scratch. So what happens at that point is that all of those algorithms, their performance drops down because they have to adjust to a new filter, and then they start adapting at it again. Now, our approach is the one shown by the light blue. And as you can see, we're many decibels better than all of the other sort of standard approaches. And the reason why that is because it's a system that's trained and specifically optimized to do its best possible job for that problem. Which means that we didn't have to use any heuristics. It's not a sort of a standard deterministic algorithm. It really tries to sort of really solve that particular problem. We noticed that in terms of ERLE, it's doing a lot better. You can also see that it's adapting a lot faster, which is the goal that we had starting with this problem. And if you look at things like STOI, which is a measure of speech intelligibility, we also see that it's doing a lot better than all of the other approaches as well. So the good news is that it's really outperforming sort of the hand designed models and all of the algorithms that have been fine-tuned by hand. And we didn't have to think particularly hard to do that. We just had to train a neural network to do it. We just didn't have to train a neural network that does the echo canceling itself. We just had to do one to do the optimization. So the take-home message here is that you shouldn't necessarily replace all of signal processing with neural networks. What I've been seeing a lot being published right now is, let's make a big neural network that learns how to do echo canceling. You don't have to do that because that requires a lot of data. It's going to be a lot more complicated. It's going to be very difficult to control in terms of stability. Instead, what we're going to do is we basically replace the optimizing part, which is where the actual engineer has to come in and sort of think, and we're replacing that with an intelligent system. So the advantages is that it works better than even full-fledged neural network models. It's a fairly small neural network. It's really very, the computation is not significant, and it can train on a very small amount of data, which again, a full-blown neural network system that has echo cancellation would require a lot of hours of data. This was done in less than 1 hour of data. And of course, what's nice is that you can use the same idea and adapt it to all sorts of different adaptive filter cases, right? You can do that for equalization, denoising, the reverberation. And for all of those that we tried, we keep getting a better performance. So that's very exciting, of course, because it means that there's a lot of advantage, a lot more performance to be gained by coming up with the right optimizer with just a simple update to standard adaptive filtering. Normally, I would pause for questions, but I guess I'll go on and sort of save them all for the end. So now, part C, I want to talk a little bit about scaling. And the idea behind scaling is that we want to use algorithms that can scale in terms of the hardware that we're using. Like I mentioned before, with the idea of the hearables, we want to be able to have a device that can fit in your ear and do the processing. But maybe you want to do some of that processing on a laptop computer because you have connected headphones to it, or maybe you want to do this processing on the cloud and then stream it to the device. So being able to use the same algorithm with sort of different devices and different computational complexity is something that's very desirable. And that's sort of the goal of this part. Now, what we're going for with point audio processing is the idea that we want to liberate ourselves from fixed representations of audio. So if you think about a lot of audio processing algorithms, they're always using very consistent or very, very fixed representations. For example, if you're operating in the time domain, you have a vector that contains your sample data, and maybe you're taking frames of that to process. Or if you go in the time frequency domain, maybe you do a short-time Fourier transform, and then you have this fixed size frames that you're processing. Either way, we tend to think in terms of having our data as a vector or a matrix or a tensor, because that's the sort of legacy of MATLAB, right? We all started thinking in terms of that kind of data representation because that's what the CPUs and the GPUs are best at or have been designed to work with. But the problem with those representations is that they impose a lot of limitations. When you learn an algorithm that operates on a Fourier size of 1024, then you're stuck to that size. You can't change it very easily. So what we want to do is sort of explore different ways of representing sound that will give us more flexibility, which means that we'll be able to adjust our processing and change sampling rates and change the sizes that we operate on without having to change the algorithms. And that's the idea behind the point audio processing. So let's look at fixed dimensions. Standard sort of machine learning approach is that you take your data, you represent it as a vector. It's usually going to have some fixed dimension n. Most of the algorithms, if not all of the algorithms that I know in speech and audio, start with that kind of assumption. And the bad thing is that once you learn an algorithm that works in that space, it's very difficult to use a different kind of representation, right? If your input size is fixed, you're stuck with it. So you cannot change your representation. If you try to operate on a different sampling rate, again, that's going to be a problem. And then you're also tied to sort of vector processing architectures, which it's fine for a desktop, but not necessarily fine for other types of processing. So instead, what I'm going to advocate for is using non-fixed size data. So let me give you an example of that. What you're seeing on the top plot here is a spectrogram of just some speech. And again, if you've seen those a lot, you'll probably notice that you can see some of the harmonics, you can see some of the Foreman structure. It clearly gives you a nice representation of what's going on in that space. An alternative representation of the same data would be in terms of what we call a reassigned spectrogram. Now, what a reassigned spectrogram does is that it takes every pixel of a regular spectrogram, and it does a computation to basically fine-tune its exact frequency and time location, and it takes that sort of a pixel and makes it a point that lives in a real valued frequency and time space. So if I were to plot a reassigned spectrum, it would look like the bottom plot. And what you're seeing here is basically the same data as in the top plot, but each square that makes up the picture in the top spectrogram has now become a point, and that point is indexed by a real valued frequency and a real valued time. So our representation is actually going to be a set of points that will have real valued coordinates as opposed to integer valued coordinates, which is what we had in the regular dense representation. And the number of points could be variable because we can decide to keep maybe half of them or only the loud ones or any kind of subset. Now, what's nice with that representation is that it's mostly sample rate invariant. What that means is that if I were to change the sampling rate of my representation, these points would be roughly at the same spot because they're being indexed by hertz and by seconds. So we don't have to index them in terms of the sort of FFT bin number or sample numbers. And we don't have to use all of those points. If I have a device that does not have a lot of computational power, I could use maybe 10% loudest ones, or maybe I want to use all of them. So it's a very flexible representation, but the problem that this representation has is that it's very difficult to plug into a standard algorithm. So what I'm going to be advocating now is sort of trying to think of standard audio processing in that concept. So our data now is going to be represented as a vector set. And that vector set is going to have a whole bunch of samples indexed by I, where we would have, in this case, just a three-dimensional vectors. We're going to have one dimension being the frequency value, that's going to be in hertz. Another element is going to be the time value in seconds. And the third one would be the complex value of our that belongs to that point, right? The magnitude or the phase, for example. So we're going to go from a representation that's a regular grid where every point had an integer valued address to a set of points where now the address is going to be a real valued number because it's not going to be in terms of the bin number. It's going to be in terms of hertz and seconds. So what's nice is that now we're breaking free from the idea of having a fixed sample rate. Our data could be any kind of sampling rates, and our data set could have any size. It doesn't have to be a fully provided dense matrix presentation. So now the problem is we're going to have to find ways of processing that data. Now, if you look at a traditional algorithm, it's going to rely on fixed sizes, right? So if you have, for example, a classification, the way that it would work in a regular setup is that you would give it your matrix representation of, say, your spectrogram. You would have some kind of a sort of vector that gets multiplied with it. You're taking dot product, putting it through a nonlinearity, and that's a simple classifier. You cannot do that with point data because now you don't really have a matrix structure. You don't have a finite number of I's because your frequencies are going to be real valued. So now the representation or the processing is going to be a little different. We're going to have a set of points, and each point is going to correspond to each one of those dots that we have here. These points are going to have a real valued frequency, real valued time, and then real valued sort of a feature value. And then what we're going to do is we're going to process all of those points with a linear transformation. We're going to have some kind of an aggregating function that basically applies some kind of a nonlinearity or some kind of a pooling over all of those transformations, and then we're going to take the sign of that. Right, so that's a standard way you would process point data. So let's look at how this thing would work in a real life application. So we're going to take a sound recognition task. In this case, we're going to do the ESC10 problem. So we have 10 different types of sound classes. And then our sound data is going to be represented as a set of tuples. So it's going to be three-dimensional vectors that are going to have real valued frequency, real valued time, and then the amplitude at the corresponding time frequency point, right? So it's basically going to be the points on this bottom plot down here. So it's not going to be a matrix input. And then we're going to compare that to a baseline conventional a CNN model that operates on the spectrogram. And in our case, we use a cell transformer, which is basically a slightly more elaborate version of the processing that I have here. So there's 2 points that I want to make with that. The first one is shown in this plot, and there's a lot of stuff being shown here. So let me slowly walk you through it. What I want you to focus is 2 things. The first one is that on the x-axis of this plot, I'm showing a window size, and this is how many samples was I processing at any point in time. Now, for the fixed network, it was, for both actually, it was trained on windows of time that were 2,048 samples long. What that means is that if I were to give it sort of input frames of that size, it would be able to give me a classification output. I could potentially give it smaller sized inputs if I were to do zero padding in the frequency space, and I could still sort of zero pad to a size of 2048. And if I do that, it doesn't really change the performance too much. But if I were to provide it bigger time windows, this algorithm cannot do anything with it, right? It doesn't know how to process data which uses more audio. On the other hand, the algorithm that we're using, we can definitely give it a window size with more samples, and it has no problem digesting that data. In fact, it doesn't seem to hurt the processing that much. Now, the other thing that you're seeing is that you're seeing 4 lines that show you the accuracy. And again, the higher the lines are, the better the performance is. What happened in this case is that we trained our system at a sampling rate of 44.1 kilohertz, but then we also evaluated it at lower sampling rates. Again, with the standard algorithm, we see that the overall performance is not as high as the model that we propose, but we also see that if you lower the sampling rate, there's a huge drop in performance. It doesn't operate as well because this is not an algorithm that knows how to deal with different sampling rates. Whereas the degradation that we're seeing in this case, because our data is represented in terms of hertz and seconds, is not as bad as in the other case. The other thing that's interesting is that our proposed model is about half the size of the CNN model, and it still outperforms it by a fairly wide margin. So we're getting some nice invariance here. But the second point I'd like to make, which I think is very important, is that we don't even need to keep all of the data. If I go back to the representation that I have here, I could throw away most of the data in this plot, and it would still communicate pretty much the important information. And what we've figured out is that, and sort of shown in this plot, is that if we start throwing away some of the data points that are used in the input representation, we try to measure the performance, and what we notice is that we can even keep down to 20% of the points that we have in our representation, and we're still performing really well. Whereas if we start throwing away time frequency bins with a regular CNN model, we can see that we have a more constant degradation of performance. Whereas in our algorithm, we don't really see a degradation in performance until we throw a substantial amount of data away. Now, why is that nice? Because in terms of scaling, it means that I could have an algorithm that operates with just 20% of the data, just because the hardware might not be able to support more, and it'll be able to actually do a good job. Whereas with a traditional algorithm, this would never been the case. So the take-home message from the point audio data processing is that it usually pays to think of other ways of representing audio data. Let's not be stuck in this sort of vector matrix tensor kind of packaging. Thinking of audio in this way just gave us a lot of advantages when it comes to processing, and you can extend that to more interesting things for using, for example, graph representations, and you can do a lot more interesting processing. So again, I expect to see a lot of interesting stuff sort of following up on this. All right, and then finally, the fourth part, I want to talk a little bit about distributed self-learning, because that's going to be again another key problem in the overall hearables setup. So the problem that we have here is that because a lot of the algorithms that we're using tend to be very data hungry, we usually require a lot of training data. And that's a big problem, right? Because it means that you have to collect the data, which again comes with a lot of interesting sort of privacy concerns and stuff like that. But then you also have to spend a lot of time labeling the data and cleaning up the data. And this is something that takes it takes a lot of time if you work in audio processing, and it's something that a lot of people would rather avoid. Especially if you're an academic like me, it's a big problem because I don't have the abilities that Amazon or Google or Facebook have to collect huge data. it's just something that I can't compete in. And of course, given that we have algorithms that their performance depends mostly on the data they're being trained on, it's really a huge disadvantage for the academic community. So what we'd like to do is to be able to learn from data that we record just in the wild, not necessarily from sort of curated, collected data collections. And that way we can bypass privacy concerns. We can make sure that the data matches the distribution of what we actually want to, where we want to deploy a lot of those algorithms. And so in this sort of final part of the talk, I want to talk about how we can do that in a distributed way and how we can do it with a self-learning system. So the learning process that I'm trying to advocate is taking advantage of the current situation, right? You know, I want you to look around you and sort of try to figure out how many microphones are near you, right? I mean, right now in my office, I could, you know, my laptop has a couple of microphones, my camera has some microphones, I have a phone, I have my watch has a microphone, there's a tablet with some microphones there, there's a speaker that has a microphone. There's a lot of microphones all around us. And all of those are, you know, some of them actually capture audio and sort of analyze audio as it happens. So what we'd like to do is take advantage of this availability of audio data. But the wrong way to do this is to basically take that data, store it, or maybe transmit it over to some company's hard drive. What we'd like to do is make algorithms that locally adapt and try to perform their task without having to centralize a data set. And that bypasses a lot of practical problems when it comes to privacy and data collection, but it's also something that I think is a much more elegant way of learning. You want to be learning as you're being exposed to the data, as opposed to learn offline and then switch into an inference mode. So the example I want to give you is going to be that of speech enhancement. And the question is, can we make a system that can improve the quality of a speech recording from just listening at a lot of speech, not necessarily being guided by trained data? And we want that to happen with multiple devices which are not strictly coupled with each other, but you know, loosely communicate every now and then. The idea again would be that if you have multiple people that have devices like that, you want them to be able to sort of use each other's learned sort of machine device experience to improve the algorithms. So this is going to be split into two parts. The first part is talking a little bit about how we can learn just from mixtures. And then I'll talk about the distributed part. So how do we learn only from mixtures? So one thing to note is that a lot of these sort of modern enhancement systems need to have what we call oracle data. So the usual setup is that you might have a lot of noisy recordings of speech, for example. So you know, you have the noisy recordings, let's say those are Y of T, and then you have a speech component in it, and then you also have a noise component. Well, the only way to train a deep neural network, or at least the most common way to train a deep neural network, is to actually have access to the clean speech data as well. So the standard thing to do is you get a big database of just clean speech recordings, you artificially mix them with noise. So now you have this set where you have noisy speech, but you also have the clean speech for those recordings. And if you do that, it's fairly straightforward to train a system that tries to map the noisy speech to the clean speech. Now, the problem with that is that you need to have a lot of data. And the data that you generate might not necessarily match the distribution of the data that's out there in the real life. In fact, it almost never does. And it becomes a very complicated sort of engineering process. So instead, we're going to use a process that's going to be learning from mixtures. And that's going to go as follows. It's sort of an algorithm that hinges on another algorithm. So it's probably going to be a very high level overview, but I just want to give you the basic idea. We're going to start with a model that we're going to call the teacher. So this is going to be a teacher-student model. So we're going to be calling that F of T over here. That can be a pre-trained model, or it can be a model that learns by itself. But the basic idea behind it is that let's assume that we have a neural network that can perform, for example, speech enhancement. And what we're going to do is we're going to give it a bunch of real-life mixtures. We want this to produce its best guess for the speech and the noise sources. And that doesn't even have to be a neural net, right? It could be a sort of a standard denoising algorithm. And then once it does that, we're going to take those estimated speech outputs, which are not going to be perfect. We're going to take the estimated noises. We're going to permute the noises and change the order, and then mix them back together with the estimated speech. And then we're going to train another model. We're going to call it the student model on these new mixtures. And now we're going to give it as targets the extracted speech from the original model and the noises as we permuted them before. So what we're doing is sort of a two-tiered process. Now, it turns out that if you do that, so that's known as the remixed algorithm. And it turns out that if you do that, you actually end up improving significantly on the performance of the teacher model. Now, how does that work? Well, the teacher outputs are going to be imperfect, right? But they're still going to give you a little bit of information on what's different between speech and noise. And what the student model does is it's trying to latch on those things that matter and are consistent across all the training example to help it improve its performance. Now, how well this works is dependent on many variables because you can have the teacher also be dynamically evolving as well. You can have sort of your training data set for the teacher or your initial state for the teacher might be matching a lot of the data that you're seeing or not. So there's a lot of things to worry about. But in general, we ended up seeing performance from about 1 decibels up to 8 decibels in a signal to in SDR, signal to distortion ratios, which can be significant. Now, what's interesting is there are 2 ways to run this kind of algorithm. We can run this as a semi-supervised learning setup, which means that we have a trained teacher model, and then we're collecting data, from devices in the wild, and their distribution is not necessarily going to match the teacher. And then the student model tries to figure out how to best deal with this new kind of data given the experience of the teacher. So that's one thing that we can do, and that gives us about 7 to 8 decibels of improvement. Or we can have a completely unsupervised system where the teacher could be trained using the mixed algorithm, which is an unsupervised sort of enhancement algorithm in sort of unrealistic type of data, and then we can use the student model to sort of refine that with data that we can capture in real life. And again, doesn't give us as big of a performance if we do that, but it's still a significant one. It goes up to 6 to 7 or 7 decibels SDR. We can also have systems where the teacher is being updated over time. Again, that could give you better performance. So there's a lot of variations. So now we can try to put this thing to work. So we can take that algorithm, we can take a whole bunch of devices, let's say smart speakers all around the world. We could put a voice activity detector. So that means that they can start collecting a lot of those data. And now we want to federate this type of learning. And the idea is to keep the training data in the recording devices. They're going to learn their own student models. And then every now and then they can communicate with each other to update things. And the way that would work is we could have all of those nodes. They're all trying to independently improve themselves. And in our experiment, what we've done is we had them trained for about for a while, and every 6 hours, a quarter of those devices would exchange their models with the other devices, not the data itself, and then they would get updated, and then we'd sort of go at it again. And we did this for about 1,000 times. And I'm almost done. I see my moderator is making his presence felt. What we get out of this process is that sort of shown in this graph. So what I want you to focus on is the dark line is going to be the upper limit, where had we known all of the training data, this is the performance we would expect to get. The 3 colored lines that you see, sort of continuous lines that you see here, is the case where we had 256 groups of devices, 64 groups of devices, or 16 groups of devices that were learning and sort of helping each other. And what you're seeing is that as time went by, the performance of those models, even though they were training locally with their own subset of data and not necessarily sharing any data at all, it's starting to approximate the optimal performance had all the data been known. So what's really nice, it means that we don't really have to have systems that learn on one big database that's being shared across everything. We can actually be collecting data in real time all over the world and then slowly updating some of those models. And we know that this is going to start tending towards doing the right thing over time. Which is really nice because it helps us with privacy and matching distributions of data and stuff like that. So the take-home message from this last part is that we don't really need to train offline large data sets. We don't need to gather data centrally. And what I like about it is that it's really starting to approximate the idea of learning from listening, which is, again, one of the big sort of science questions that I want to solve. So to start wrapping up, the suggestion I'd like you to take from this talk is find a difficult problem that you cannot solve. And then that's going to help you find a lot of interesting problems to solve. Don't try to find problems that you can solve, because then that's not going to be particularly interesting, because then you know how to solve them. Try to keep away from chasing metrics. Try to think of orthogonal ways from what everybody else is doing. And I think that's really where a lot of the interest in papers is. Again, I would totally urge you to avoid using yet even bigger data sets and bigger neural networks. There's a lot of interesting stuff to be done otherwise. Finally, just to give credit to my awesome students that have done most of that work. I'm just supervising. They do all the great work, and of course, to our supporters that finance our research. That's all that I had to say, and thank you for listening. And I'm happy to answer any questions, either now or feel free to send me an email as well.